Hey folks, my name's Ivan, and on this channel I'm going to be making overviews of machine learning research papers with a particular focus on model compression, acceleration, and inference optimization. So subscribe and stay tuned for more content like this, and smash like if you feel like it. And the topic today is GhostNet V2, enhanced cheap operations with long-range attention. So this paper proposes a lightweight DFC attention module for convolutional neural nets. And this is a generic technique that can be applied on top of any CNN, but here authors build on top of their GhostNet paper. And their claim that adding DFC attention to GhostNet actually gives you a boost of around 1% on ImageNet. So they were able to achieve 75.3%. Importantly, they say that the DFC attention mechanism is hardware friendly as opposed to the traditional self-attention mechanisms used in transformer backbones. So the authors compare GhostNet V2 in terms of accuracy versus speed to other CNN models that were designed for mobile hardware deployment. And they provide these trade-off curves for accuracy on ImageNet versus flops and latency. So the latency here was measured on a Huawei P30 phone with a Kirin 980 CPU using TF Lite as an inference engine. So the authors clearly show that GhostNet V2 is superior to these other models in terms of accuracy versus speed. Unfortunately, they didn't add some of the vision transformer-based models to this plot. Like here, for instance, they say that the recently proposed mobile VIT architecture has massive self-attention operations, and in terms of theoretical flops, it shouldn't be that bad, but when actually benchmarked on ARM processors, it's 7 times slower than MobileNet V2. So to kind of overcome this problem of long-range attention operations being very costly on mobile hardware, they propose this new attention mechanism called DFC. And they're saying that GhostNet is essentially state-of-the-art, and they apply this DFC attention mechanism on top of GhostNet to get the GhostNet V2 architecture. So first, they review the GhostNet paper, which is a state-of-the-art lightweight model. It's a paper from 2019, and so the gist of this paper is to replace the traditional convolutional operation with the subgraph, where they say some portion of the feature maps is going to be generated by the same convolution with the same kernel size, but then the remaining feature maps are going to be generated from the already computed feature maps with some lightweight operation, which in their case is just a depthwise convolution. So basically, these features are being concatenated with other feature maps, which are computed with a depthwise convolution here. So this is kind of a lightweight drop-in replacement for any convolution layer. The same thing is briefly described here. And they're saying that GhostNet is constructed by stacking these Ghost modules in a Ghost bottleneck. So next, the author lay out this problem of self-attention being very costly in terms of latency. So one can see that the theoretical flops of GhostNet and GhostNet with self-attention are not that different, but it's almost 2 times slower. And they say that with their DFC attention, the accuracy is even higher. The flops are comparable, but the latency is actually only a bit higher than the original GhostNet. So the features of this DFC attention are that it is long range. It's able to capture like long range spatial information from the feature map, as opposed to a convolution that has a 3x3 or 5x5 window of context. It is deployment efficient because it doesn't have a lot of the reshaping operations that are typically associated with inserting a self-attention block into a CNN. So this DFC attention only has like fully connected layers. So the way they compute this DFC attention is they first look into applying a fully connected layer to the feature map Z, treating each of the pixels of the feature map as a token. So this results in a quadratic complexity of this operation, which they say is unacceptable in practical scenarios. So after that, they kind of look into decomposing this fully connected operation into horizontal and vertical aggregation, which follow each other. And after that, they kind of reduce this to a stack of two convolutions. One is of kernel size 1 by kh, and the other is of size kw by 1. So this is a sequence of two depthwise convolutions with these horizontal and vertical kernels that are sequentially applied in the input feature. And so they say that the input feature is sent to two branches. One is to like a convolutional operation or a ghost module, and another one to this DFC attention module. And they also recall that in a typical self-attention layer, you would have a linear transformation first to transform your input to query and key. So they mimic that with a one-by-one convolution, and then they pass this through this stack of two depthwise convolutions, horizontal and vertical. And then the final output of this operation is passed through like a sigmoid function to produce this attention map in the ranges from 0 to 1. So another thing they apply here is downsampling. So they say that applying DFC attention as described is prohibitively in terms of computational cost. So that's why they first downsample the feature map, then apply all of these one by one depthwise convolutions, and then they upsample it back to the original size to kind of match the size of the output of the other branch. They can do the element-wise multiplication. So in code, it looks like this. They have the PyTorch implementation for this Ghost module V2. So this is a modified implementation of the original GhostNet module. So they have this flag, which if set to original, performs the original GhostNet operation, which consists of a primary convolution and this depthwise convolution. So primary convolution is just a sequence of convolution batch norm and ReLU. And the cheap operation is just a depthwise convolution. So they pass the input x through this primary convolution to get a portion of the feature maps x1, then x1 gets passed through the depthwise convolution to get the other portion of the feature map x2, then they just get concatenated. So in case the mode flag is set to attention here, we have both the DFC attention and the Ghost module at the same time. So this part of the code is just implementation of the Ghost module, and this part is related to the DFC attention, which can be also distilled in a single PyTorch module. So the input x is first downsampled with an average pooling, then it goes through the short conv module. So short conv is just this one by one convolution followed by a sequence of horizontal and vertical aggregations, which are done through the depthwise convolutions of kernels 1 by 5, 5 by 1. Here it's hard-coded. And then once we get this result of the short conv module, we pass the result through the activation function, which is a sigmoid in this case. So the gate function is just sigmoid. It can be like a hard sigmoid or ReLU. Then we also interpolate to match the size of this output of the Ghost module. And then we just perform element-wise multiplication. So this is essentially GhostNet module V2. And that module is just used to form the Ghost bottleneck and eventually GhostNet V2 architecture itself. In the experiment section, they also look at whether GhostNet V2 can act as a good backbone for detection and segmentation tasks. So they use GhostNet V2 in a Yellow V3 detection architecture as a backbone. And they just compare to GhostNet V1 and MobileNet V2 and see that they have a higher average precision on the COCO dataset, which would be also interesting to compare against the traditional backbones used in the LV3, such as CSP DarkNet 53, whether GhostNet V2 would be a better choice of backbone in terms of both MAP and speed. So they also have an ablation study of DFC versus other attention mechanisms developed specifically for convolutional models, such as squeeze excitation blocks and CBAM. They show that DFC gets you better accuracy applied on top of MobileNet V2. So this is a generic thing that can be applied to any mobile architecture you can try out for yourself for your custom architecture. In terms of semantic segmentation, they also get a better MIOU score using GhostNet V2 as a backbone in DeepLab V3 on the ADE 20K dataset. And finally, they also look at the impact of kernel size in the DFC attention operation on accuracy. So they reach better accuracies with the larger kernels. And they also look at how the choice of the gating function in the DFC attention module influences both accuracy and latency. So in their case, sigmoid versus hard sigmoid versus clip didn't have a lot of difference in terms of latency. And in terms of accuracy, there's about 0.4% difference between sigmoid and clip. And they also compared their vertical/horizontal attention to the case where we have the full attention. And they kind of show that the attention maps formed in either case are quite similar to each other. So that's it for the GhostNet V2 paper. It's really cool that we have this lightweight alternative to self-attention for convolutional neural networks. Would have been cool if the authors added more data points to these accuracy versus latency curves. Like, for instance, you can take data from the TIM repo, given that it's publicly available for ImageNet, and you could add a lot more up-to-date state-of-the-art models in its graph and compare, for instance, to some of the transformer-based vision models that came out recently, as well as some non-transformer ones like Mobile One from Apple, which I think would be a very relevant comparison here. Another thing that I wish was in the paper is more comparisons with other backbones with DFC added on top. So it would be cool to see how DFC boosts accuracy for different families of CNN architectures. But I thoroughly enjoyed this paper, and I hope you did too. Smash like, subscribe, and till next time.